Hello everyone. Welcome to the fourth lecture of power system stability. Here we discuss the concept of synchronizing and damping torque. We know that the electrical power output of the synchronous machine is equal to E into V by Xs into sine del, where del is the angular displacement between E and V. The power angle del was discussed in the previous lecture. Please go through that lecture. And E is the induced EMF and V is the terminal voltage. Now let's see the plot of del versus PE, or power angle versus electrical power output. It's half the sinusoidal cycle, because when del varies from 0 to 360 degree, we have a full sinusoidal cycle. Here del varies from 0 to 180 degree, where we have the half cycle, and the crest of this half cycle corresponds to del equals 90 degree. Now let's see a scenario in which the machine initially operates at an angle del 1, the power angle del 1, and the corresponding electrical power output is PE1. Now, if the machine is operating in steady state, then at this point PE1 is equal to PM1, or electrical power output is equal to the mechanical power input. So there is no acceleration, there is no deceleration. Acceleration and deceleration are zero. Okay. So from this point, the disturbance considered here is the increase in mechanical input from PM1 to PM2. Okay, the mechanical input is increased from PM1 to PM2. So while increasing the mechanical power input, the electrical output still remains the same at PE1. So the machine naturally accelerates, right? Because PM1 is greater than PM2 is greater than PE1, so the machine accelerates. So when the machine accelerates, the angle del 1 will increase to angle del 2, right? Because now the electrical power output will increase. Accordingly, sine del will increase and del 1 will increase to del 2, or vice versa. If del 1 is increased to del 2, then PE1 will increase, right? So what happens here is the machine is initially operating. Once again, I'll repeat this. The machine is initially operating at del 1 and PE1, right? Del 1 and PE1, and the mechanical input is PM1 at this particular point, where the machine is operating at steady state. Then the corresponding torques are, we know that force into velocity is power. In rotational motion, it is torque into angular velocity, which is power. So torque equals power divided by angular velocity. So mechanical torque is PM1 by omega at this point, and electrical torque is PE1 by omega at this point, right? So but initially we have mechanical torque equals electrical torque, and there is no acceleration or deceleration, right? Now that is why here it is written Tm1 equals Te1, implies Ta, acceleration torque, equals 0, no acceleration, and the machine is at constant speed now. Now let's see this axis. So this red colored line represents the stator magnetic axis, which is taken as a reference. Now initially the machine operates at del 1, so the rotor angular position is 2, corresponds to this 2, position 2. So the angle between these two, the dotted line and the reference stator magnetic axis, is del 1. Now when PM1 is increased to PM2, we have acceleration and the rotor accelerates, so del 1 is changed to del 2. So the relative angle between the physical rotor axis and the stator magnetic reference axis is increased now. So because of this increase, PE1 is increased to PE2. PE1 is increased to PE2. Now we don't have control of the stator magnetic axis. We have control over the rotor axis, physical rotor axis only. That's why we have taken here the stator magnetic axis as the reference. And any disturbance in the machine, any disturbance applied in the system is represented by variations of del with respect to the change in position of the rotor axis only, by keeping the position of stator magnetic axis constant, or keeping it as the reference. Now we need to feed more load, which implies del 1 is moving to del 2, right? When del 1 moves to del 2, we need to feed more load because electrical power output is increasing, PE is increasing. Now suppose the governor valve is opened more so that PM1 increases to PM2. This is the case we are discussing now. From the initial operating point, PM1 is increased to PM2, but PE1 remains the same. So there is TM2 greater than TE1, because TM2 corresponds to the new PM2, which is greater than the PE1. So TM2 greater than TE1, and TA is positive, acceleration torque is positive, which implies the rotor accelerates. So del 1 is moved to del 2. With respect to rotor axis in figure 2, here with respect to rotor axis there is a change, right? Or I mean with respect to the reference stator axis, the rotor axis is moving. Okay, now sine del increases, so PE1 increases to PE2. This change in electrical power is known as the synchronizing power. That means change in electrical power in the sense new electrical power is PE2. The initial electric power output was PE1. So PE2 minus PE1 is the extra power required to bring back the generator to steady state condition. Because initially PM1 was moved to PM2, right? At that time PE1 was the same value. It was not changing, right? Now PE1 is going to change to PE2, so that delta PE, or the extra power required to balance the electrical power and mechanical power, that is to bring back the generator to the steady state condition. This is known as a synchronizing power. So the delta P is the synchronizing power, which is dP by d del into delta del, which is dP itself basically, or delta P itself. Okay, so how to evaluate dP by d del? P, we know that P is EV by X into sine del. So if you differentiate it with respect to del, then d by d del of EV by X sine del we have to take. That will give you EV by X cos del into delta del. So the synchronizing power is now represented in terms of EV by X into cos del into delta del. Here this EV by X cos del is in watts per radian. What is watts per radian? What is the meaning of that? If there is any variation in del or power angle, how much is the corresponding variation in power? That is watts per radian. Unit change in radians, I mean unit change in power with respect to unit change in radian. Okay, so if it has to be converted to degree, then multiply this with pi by 180. If this is multiplied with pi by 180, you can convert this to watts per degree. Now, if this electrical degree has to be converted to mechanical degree, then multiply further by pole pair P. Okay, this we have already seen in the previous lecture. Now, EV by X cos del in equation 1 is known as the synchronizing power coefficient. This one, this is the EV by X cos del, gives you the synchronizing power coefficient. When del increases, cos del decreases and synchronizing power coefficient decreases. That means rigidity or locking effect between stator and rotor is weakened. Right, rigidity or locking effect between the stator and rotor is weakened. The machine is prone to asynchronism. The system is prone to asynchronism. Now substitute del 2 minus del 1 for delta del in equation 1 here. Here instead of delta del we substitute del 2 minus del 1. When you substitute del 2 minus del 1 for delta del in equation 1, you get the synchronizing power delta P, because this equation itself is for synchronizing power delta P. So dP by d del into del 2 minus del 1. For dP by d del we substitute EV by X differential of EV by X sine del, which is EV by X cos del. So EV by X cos del into del 2 minus del 1 will give you the synchronizing power. Okay, now if you want to find the synchronizing torque from synchronizing power, power divided by angular velocity will angular speed will give you the torque, right? So angular speed is here synchronous speed itself. So delta P divided by omega s, this will give you the synchronizing torque. So this is what is the concept of synchronizing power and synchronizing torque. Now we will see in the coming lectures the concept of damping power and damping torque also. Thank you.